Hello students, now let's take the next definition of minimally connected graph. Now in previous video we have seen the definition of tree and few properties of it, right? So let's see first of all here the definition of minimally connected graph. Later on let's see again few properties. Okay, so a connected graph G is said to be minimally connected. If G minus singleton E is disconnected. G minus singleton E is what? Disconnected for any age E in what? G. As I have shown by taking an example of T3, if we will eliminate this age, then that will become a disconnected graph. Minimally disconnected means if we remove a single edge from it, still it will become a disconnected. So it is minimally disconnected graph. For example, now if we take this one, suppose these many vertices and the edges are as such, these are connected. Now if I remove one of the edge from here, either this one, then it will become isolated. If I remove this edge, then this graph will be separate. This is separate. If I remove this edge, then this is another part, this is another part, right? Similarly for other also. So if I remove a single edge from it, then it will become a disconnected graph. So this graph is what? Minimally disconnected. Minimally connected, we can say. It is disconnected means minimally connected. Now on the contrary, if I take this one, suppose I have this graph, then look at this. If I remove the edge from it, then it will become a disconnected? No. Similar for other also. If I remove this one, then is it become a disconnected? No, right? Now if I remove this edge, then it will become disconnected, but it should happen for every edge. For any edge this should happen, then it will be minimally connected, right? It is not for any edge, it is for this one edge only. That's why this is not minimally connected. While here, if we remove any edge from here, it will become a disconnected graph, right? So this is not minimally connected. Now let's see some properties of trees and a minimally connected graph. This is also one of the tree. Look at it carefully, right? So let's see few of the properties. Further, let's continue. Theorem: a graph G is minimally connected means G is what? Tree. G is tree. So proof: if and only if it is a tree. So both way we have to prove, right? So for if G is, we will assume this part first, G is minimally connected. G is minimally connected, so means G is connected. G is connected. Again I will repeat, as we have to show G is a tree means we have to show it is connected and circuitless. Now it is minimally connected means it is connected. There is a path between any two vertices of a graph, right? Also G cannot have a circuit. G cannot have a circuit. If G has a circuit, say C, and if E belongs to C, then G minus this E is still connected. This will happen, it will be still connected, right? Is it fine? G has a circuit, say C means it has a circuit. For example, this one, suppose G has a circuit. Now if we remove the edge E, still it will become a connected, but as it is minimally connected, so if we remove any edge from there, it won't remain connected, it will become disconnected that time, right? So here if it has a circuit and if we remove an edge, then it still remains connected, which is a contradiction, to the definition of minimally connected, or to the minimally connected, I can say, to the minimally connected, right? Therefore G is connected and circuitless, On a contrary, now the converse part, let's see, that is G is tree. Now in converse part, it is given to us G is a tree, right? Conversely, G is a tree. If it is a tree, then E is what? Suppose any edge in G, Therefore, if we find T dash will be, or let it be G dash will be what? G minus this E. This A and B are what? In G dash. Fine. So, if this graph we will form, if we eliminate an edge from tree, then it gives us this G dash is what? A disconnected graph. It is disconnected. As we have seen in first property, that if we form G dash by removing an edge, then that will become a disconnected with components, with two different components, right? Same thing is here also. G dash will become disconnected, and if it will become a disconnected for any edge, then that is what? A minimally connected. Therefore G is minimally connected. This is the proof. We have to show if G is minimally connected, then G must be a tree. So we have proved it. This is first part, and this is a second part, that is converse part. Okay, now the next theorem. Let's take the next theorem. Next theorem says that a graph G with n vertices, n minus 1 edges, and no circuits is a connected graph. Okay, proof. Suppose G is a circuitless graph. G is a circuitless graph with n vertices and n-1 edges. What is our claim? We have to prove that G is connected. G is connected. Okay. So now let's prove this by contradiction. Proof by contradiction. So on a contrary, let's assume, suppose G is disconnected. G is disconnected with at least two components. With two components, say G1 and G2. Say G1 and G2. Now let me give a figure. Suppose here G1, here suppose G2, and here is a vertex U and here is a vertex V. Okay, and there is an edge in between them, suppose E. Now let U in vertex set of G1 and V in vertex set of what? G2, right? Add an edge E between two vertices, say U and V. As I have shown in diagram, I have added an edge in between them, right? Since there was no path between U and V in G, there is no path between U and V in G. But by adding an edge E, it didn't create a circuit in G. There is no path in between these two vertices, and if I add an edge in between them, then there is no circuit, right? Adding an edge E didn't create a circuit. Didn't create a circuit in G. So what does this gives? G minus this E, that is G dash, is connected circuitless graph with n vertices and n edges. N vertices and n edges. That is, G dash is a tree with n vertices and n edges. If it is connected circuitless graph with n vertices, n edges, so it will become a tree with n vertices, n edges, which is a contradiction. To whom? It is a contradiction that it won't be a tree with n vertices and n edges. It is a tree, then it will be having n vertices and n minus 1 edges, right? So it is a contradiction, which is a contradiction. So why does this contradiction occur? Because we have assumed on the contrary that there is G is disconnected with two different components. Two components we have been assumed, and we have been taken two vertices and edge in between them. By taking an edge in between them, we get that here this is connected graph, circuitless graph with n vertices and n edges. So it is contrary to the fact that it is a tree. So G is what? Connected. G is connected. Fine. Now let's, from all these statements or all these theorems, G is connected, then we get some equivalent things. Let's write them. What are the equivalent things for G is a tree? For G is tree, it gives, first thing, G is connected circuitless. From definition, connected and circuitless. Second, there is exactly one path between any two vertices of a graph G. Next thing, G is circuitless. G is circuitless and has n-1 edges. G is connected and has n-1 edges. Connected and has n-1 edges. Also, G is minimally connected. All these are what? Equivalent statements for G is a tree. We can say it as such also. Now, let's see the next part, that property or the number of pendant vertices in a tree. What are the conditions for that? Pendant vertices in a tree. Suppose T is a tree with n vertices. T is a tree with n vertices. So it gives T has n-1 edges. Means T has n-1 edges, and hence by handshake lemma, what can we say? We can say degree of V1 plus degree of V2 plus so on up to degree of Vn, as there are n vertices, right, is nothing but summation of all degrees is nothing but 2 times what? Number of edges. 2 times number of edges, and that is nothing but 2 into what? n-1. So that will be 2n-2. Now you know, as we can say, note that we know degree of each vertex should be what? Greater or equal 1 for all I. Then and then it will become a tree, because if it won't be 1, then it is a disconnected graph. It should be greater or equal 1, then and then it will become a tree. There is one and only one path between any two vertices. So at least one edge in between. A degree will become 1, right? And total sum of degrees. Sum of degrees is how much? 2n minus 2. Total sum is what? 2n minus 2 is distributed among, if we distribute this among n vertices, is distributed among whom? v1, v2 and so on up to what? vn. n vertices are there. So what does this use? There are, if we distribute this thing among these number of vertices, then there are at least 2 vertices has degree 1. Has degree what? 1. That is, and degree 1 means what? Pendant vertex. Means we can say in a tree there are at least 2 pendant vertices. If between these n vertices we have to distribute this degree or this sum, then 2 vertices minimum we get having a degree 1, that's pendant vertices. So there are at least 2 pendant vertices. In a tree. This is an important thing. Remember, at least 2 pendant vertices are there. Fine. Now the next definition, let's see distance distance in a tree. Let's see first that, then further see center in a tree. So distance in a tree, let's see that part first. Distance in a tree. If G is connected graph, and if U and V are what? In vertex set of G, then distance between U and V is nothing but distance between two vertices U and V in G. That is length of the shortest length of the what? Shortest UV path, the shortest UV path in G. Length of shortest UV path in G, that is same as number of edges in the shortest UV path. Number of edges in the shortest UV path in G. In particular, what can we say? If G is a tree, then distance between U and V is length of UV path. Length of UV path. Number of edges in that one, or length of UV path. Now you should note one thing, that this distance is always what? Positive, and if the distance is 0, then you know this is nothing but U equal to what? V. This distance between U and V is same as distance between V and U, right? Distance between U and V is what? Less equal distance between U and W and distance between W and V, right? Addition. So this gives distance d is how what? This is nothing but all the properties of metric. So distance d is what? A metric. This is a metric. Fine. So now before going towards the next part, let me take one example for the distance in a tree. Now suppose we have a graph, this one, this is suppose v1, v2, v3, v4. Now suppose I have to find distance between v1, v2. So how many edges are there in between them? So that distance is how much? 1. Distance between v1, v3. Distance between v1, v3 is how much? 2. Right? Distance between v4, v3 is how much? 2. Distance between v2, v3 is what? 1. Distance between v2, v4 is what again? 1. Number of edges in between them. While going towards that part, the number of edges is nothing but what? A distance. Okay. So here I will stop. In next video, I will see the definition of eccentricity. For that, you should remember the definition of distance, this one. And then further, we have to see the center of a tree. Okay. I thought let's take the definition of eccentricity here itself so that we can go further. Now eccentricity. Eccentricity of a vertex. Of a vertex. What is the definition of it? Its definition says if V is any vertex in a graph G, then eccentricity of V is defined as what? E of V is nothing but maximum distance between V and VI, where VI is what? From vertex set of G. Maximum distance, that is maximum from what? Distance between V and V1, distance between V and V2, right, and so on up to distance between what? V and Vn. This maximum among these, where V is what? A vertex set in G, and that consists these vectors V1, V2, so on up to what? Vn. So now one vertex we will fix here. For example, from this one, look at here, this V1 we will keep fixed. So distance from V1 to V2, V1 to V3 we can find, V1 to V4 we can find. So distance from V1 to V4 is how much? 2 again, right? So this V1 I am keeping fixed. Look at here, distance from V to V1, V to V2, V to V3, and so on up to V to Vn. That is eccentricity of whom? V. I will get. So if I keep this V1 fixed here, I will get eccentricity of whom? V1. So distance from V1 to V4 is 2, distance from V1 to V2 is 1, distance from V1 to V3 is 2. So what is the maximum among these three? Maximum is 2. So I can see here eccentricity of V1 is how much? 2. What about eccentricity of V2? What is the maximum distance from all these vertices? Is 1. So eccentricity of V2 is how much? Eccentricity of V2 is 1. What about eccentricity of V3? Maximum distance from all these vertices. Here it is 1, here it is 2, here it is 2, right? So eccentricity of V3 is how much? 2. And about V4, again eccentricity of V4, if you look it carefully, from V2 it is at distance 1, but from V3 and V1 it is at distance 2. So it is also what? 2. So maximum distance from other vertex is nothing but what? The eccentricity. Fine. Now the next part, that is center of a tree, we will see in next video. Thank you.